Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. So our discussion today is going to be, of course, the activity of finding derivation of the equilibrium constant. And of course, this is going to be one of the aspects of the free energies that we are given from our first equation. Now, we have said that we can describe the free energy or the Gibbs free energy at constant temperature and pressure at equilibrium, which of course we said is equivalent to that particular value of 0. So therefore we're going to consider the general case of a reaction, whereby we're going to see that for a reaction we said that we can be able to give a general representation of a reaction using AB, which is going to result in the product of a CD. And in these specific equations there are various coefficients which we are given in terms of these small of course, representations given as such. So therefore, in our consideration of the general equation, it's going to take this specific format, and we're going to find our delta G by finding the difference between G2 and G1, of course, from this specific explanation. So therefore, I'm going to just do away with this, and we're going to consider the case of a reaction which can be given in terms of A plus B. As we said, these are the reacting species and these are the respective coefficients of those particular species. So this is a general representation for an equation that is taking place, or a reaction that is taking place with those various, of course, coefficients accompanying those reacting and the product species given as such. So this is going to continue on. Perhaps there's going to be more product given in that specific nature. But this is going to be the general equation that is going to give us an implication of the concept of course, the thermodynamic equilibrium constant that we are after. So the free energy of a product is going to be given in this particular site, and this is going to be the free energy of a reactant. So therefore, we can be able to describe from this specific coefficients and the various species that we have been given. Therefore, in this specific site for the, so this is going to be the reactant, and these are going to be our product given in this particular site. So therefore, we can be able to describe the Gibbs free energy of these two specific sites for the reactants and the product, which is going to be given in terms of I, which is a coefficient GL, plus the Gibbs free energy of M, and this particular case. So this is going to be the coefficient of a small mg, capital M given as such. And this, of course, are going to represent. So as we said, for us to find the energy of a reaction is going to be the energy of the product minus the reactant. And therefore, the IL in this particular case is going to be given by the Gibbs free energy of this specific, of course, element is going to be given by this. And the free energy of this is going to be given by this, and a various range of other products are going to fall under that specific category in case they are present. And then therefore this is going to be minus the free energy of the reactant, and we're going to have the coefficient of AGA plus the coefficient of BGB given in that specific order, and this is going to continue in case there are other reactants which have not been shown in this particular case. So therefore we can be able to find the delta G for each of these species, and the free energy is going to be given in this particular form. But we have mentioned that the free energy, the Gibbs free energy, can be given in terms of the standard state of that G not given as such, and this is going to be. So this is a particular constant, as we're going to see later, but this is the general representation of this specific equation under the standard state. So we can be able to give a version of this equation for delta G using this particular representation, whereby we're going to give it as delta G, of course, given as L. And then, so this is going to be the delta G of the products minus the reactants, whereby each of these species is going to be represented. So we're going to have this one given as L, and then this is going to be given as GL. This is a standard state, and then plus RT, the natural log of AL, and then so this is going to be the first species of this, and then we're going to have a plus m. So this is going to be m into, and then we're going to have a g standard m, and then followed by a plus r t natural log over a m given as such, and this is going to be plus other species which are going to be contained in this particular state. So this is going to be the side of a reactant, and of course I think I need it. So I'm going to use this lower space. I hope it's going to be legible. So this is going to be the side of the product given as such. So this section of the product can be given in terms of this standard state using this, and then we're going to have the reactant state given as minus. So this is going to be a of course into GA standard, and then we're going to have plus RT, the natural log over A, and then this is going to be plus, so this is going to be the second state, which is going to contain the coefficient of B into GB standard plus RT natural log over B. So this is going to be natural log over B, and then that natural log over A, and then this is going to contain that specific element of B given as B. So this is going to be a long equation, but of course you can see that each and every element of the reactant and the product have been represented using this general equation given as such, and this is going to of course be giving us this particular long equation, but we can be able to simplify this using the various laws of logarithms, which is going to give us a general representation of an equation given in this specific case for delta G equivalent to delta G standard, which is going to represent the first element, the second for the product, and the first element and the second for the reactant in that specific case. And then this is going to be RT, which is going to represent this specific element, and this one for the product, and this one for the reactant, and the natural log of so this specific section for the natural log over these various coefficients are going to be represented in terms of a ratio, which of course from the logarithms, as I've said, in case they are the reactants minus, in a minus, we are going to do a division in terms of logarithms. So therefore for this specific case, we are going to introduce the coefficient of AL to the power of L, and then AM to the power of M. Those coefficients are going to go a long way, so long as this specific condition for other products have been catered for and the reactants in that specific order. So we're going to have that one given as A, and then B given as such, and other products which are going to be accompanying that. So therefore, from this derivation, we are going to see that the natural log of this specific, of course, condition is going to be represented as such. And for a system that is at equilibrium, as we said, this specific change in Gibbs free energy is going to be equivalent to 0. So therefore, using that specific concept, I'm going to do away with this. So the value for delta G at this specific point is going to be given as 0. So therefore, we can be able to do a rearrangement of this version of the equation. So we can say that given delta G is equivalent to 0 at constant temperature and pressure, we can be able to give at equilibrium, we can be able to give this one as delta G standard is equivalent to negative RT, the natural log over L. So it's going to be small l, A capital M, that coefficient, all over A, and A, B, given as such. So therefore, this is going to represent the constant, at constant temperature, of course, at the delta G standard is going to be given as that, and of course the right hand side of this specific equation is also going to be constant. So if we try to fix this particular condition, but this constant and this are constant, And as we said, of course, from our introduction of the various variables that we use in this concept of thermodynamics, fixing two variables of a particular system, that is going to imply that the third variable is going to be automatically fixed. So if we fix this one and this one, or this one is a constant and we fix this one, then therefore this resulting, of course, aspect is going to be automatically fixed. And therefore we can be, or we can represent this specific aspect of LL, AM, all over B, and of course which is going to be fixed, and this is going to represent K, that we refer to as a thermodynamic equilibrium constant. So basically this is how we can be able to find the relationship of or derive this specific concept of a thermodynamic equilibrium by first considering a general equation of the reaction which are given for A and B, and of course finding the difference between their free energies for the product minus the reactant, and eventually employing this general representation of an equation for Gibbs free energy equivalent to the natural log of A, whereby if we consider the coefficients and of course the various species of the reactant and the product, using the laws of a logarithm, we are going to obtain this. So we see that constant temperature, this is going to be a constant value, whereby if we have R as a constant and fixing this particular variable of temperature as a constant, the third variable is going to be automatically fixed and a constant, and therefore this is going to represent the thermodynamic equilibrium constant, which we have of course derived. So that is it for now, guys. Check our description boxes for various links of other videos which are going to be related to this, and of course they are going to assist us understand better this particular aspect of equilibrium constant. So that is it for now, guys. Bye, God bless you. Catch us in our next video.